Hi everyone, Krishna this side, and in this video I'll be covering the Hamiltonian path problem from the graph. What is this exact Hamiltonian path, right? So Hamiltonian path is a path in an undirected graph that visit each vertex exactly once. So what does it mean, right? So if we have a given graph in this kind of format, so it is undirected graph, there is no directed edges here. So if we start from one, we need to visit all the vertices that are available here. So all these vertices, if we possibly visit from a particular path without revisiting the same node, then that particular path is called Hamiltonian path. So if we start from one, right, and we go downside, so if we visit one, then we visit 5, 4, 2, 3, or even 1, 5, 4, 3, 2. This is another path. Okay. So even we start from one and from this path as well, we can revisit there. Even we start from 5, there also we can get the path. From 4 also we can easily get the path, right? So there are multiple paths that are available, which conveys that it is an Hamiltonian path. Okay. So we at any point in time, if we revisit all the vertices exactly once, okay, so we are not necessarily visit multiple times, because that won't be considered as a Hamiltonian path. So in this case, like if I supposedly I start from 2, then 3, 4, again 2, 1, 5, so 2 we revisited 2 times, right? So that is not considered as a Hamiltonian path. So if in this particular example, if we start from any node, right, so even if we start from 1, then we goes to 2 or 4, and then we don't have any directed edge, or sorry, undirected edge from 4 to 3, or there is no any such connections, right? So that from any particular vertex we can visit all the nodes exactly once, right? So there is no such path in this particular problem, in this particular question. Okay. So yeah, how to solve this particular problem, right? So we can use DFS technique, right? So we can start from all the vertices and try exploring different paths, and at any point in time, let us suppose if we reach at 2, and we find that particular, we try exploring all the adjacent nodes from this particular 2, and we check that if at any point in time we are not getting the path, then we can return back and again try to explore another path. So that is the simple idea we have, and for that we use basically DFS, right? So yeah, uh, what we can do is, so if we start analyzing this, so what we can do is we can basically start from any node. Okay. So because there is no guarantee that from one, if we start, we will definitely going to get the path, right? So we can try out all the different possibilities, that whatever the vertices we have, we will try to check if there is any path available from all these vertices. Okay. And we will try all starting points that are available with us, and what we will use is we will use a visited array. Okay. So why we need visited array, right? So see, basically, if I start from 2, and then again I reach to 1, and from 1 I go back to 3, and the DFS will recursively call all the adjacent nodes, right? So for 3 there is adjacent node 1 as well as 4, then 3 again try to visit to 1, but 1 is already visited, right, from this particular path. So we need to maintain a visited array where we will get to know that okay, this particular path has been already explored, we need to check other adjacent nodes that are unvisited, right? So that is why we need the visited array. And next is like we will maintain a count variable here to track how many nodes we have visited so far, and at any point in time, if the count is actually the total number of nodes that we have, vertices that we have, if we reach to that one, then simply it is saying that definitely we reached all the vertices, and we can return back true. Okay. So we will maintain another DFS function, and in this DFS function, what we will do is, for current node, at any node that we are, we'll try to visit all the unvisited neighbors. Okay. We'll explore all the unvisited neighbors, and we mark the neighbor as visited and recursively continue with that same function. Okay. And if at any point in time count is equals total nodes, then we simply return. That is what I tried explaining you guys, right? So after recursive call unmark, we should unmark the visited nodes. Okay. The current node that we are at, we should mark it unvisited. Why I'm trying to say is, see, let us suppose now I started from 1. Okay. With this same example, I'll explain you. I started from 1. So I visited to 2. Okay. I explored for 1. What are the neighborhood nodes? 2, 5, and 3. So I explored to 2. Now once we are at 2, there are no further nodes that are that we have, and the adjacent node 1 is already visited. So in the visited array we already marked it as visited, and when we reach at 2 we'll mark it as visited. Okay, and we try to check the adjacent nodes. For 2 there are no adjacent nodes except 1, and that is already visited. So here we check that if count is actually equals to total. So in this case the count is not equals to total, right? So simply we return false. Okay, and we will mark this 2 as unvisited. Okay, so from 1 we reach to 2, and we check that there are no further possibilities available, so we mark this from this unvisited visited array. We make sure that this should be unvisited now. Okay, now again from 1 we will explore to 3. From 3 we can go to 4. From 4 we can go to 5, and now from 5 there are no any unvisited nodes that are available, right? So till here the count is actually 4 now, but from here also we are not getting any answer, so we turn back to 4 with false, and from 4 there are no further unvisited nodes, so again we return back to 3 with false. From here also it returns false to 1. So this particular path is also not possible. Then again for 1 there is 5 that is not visited. From 1 we can go to 5 as well. From 5 we can go 4 to 3, and again 1 is already visited. So from this path also the count is actually 4. We have no possible ways to reach to 2, so this will mark as unvisited. We come here, we will mark as unvisited because there are no further nodes that we need to explore. From here we go back to 5. From 5 we again come back to 1. So that is another possibility we explored from 1, and now from 1 there are no further possibilities, so this particular TFS function from 1 will return false ultimately. So 1 is completely omitted now because there are no further possibilities from 1. We will check for 2. That's why we need to check. The first thing is like we will try all the starting points. Okay, we shouldn't be rely on only one point. That's the point here. So we will check from 2. So from 2 we will go to 1, and 2 is marked as visited. Now once we are at 1, 1 will be marked as visited. We will explore all the neighborhood possibilities, so we will reach to 3. From 3 we can go to 4. From 4 we can visit to 5. Now here the count actually is equals to the total number of nodes that we have, right? So of course, if that is the condition we made, we simply return true. So once we return true, all the nodes are visited, and as soon as we are going back, we the function automatically mark them as unvisited. So it doesn't matter as well. Okay. So once we come to 4, then we come to 3, then we reach to 1, and then here we reach to 2, and ultimately this will return to true. The moment we get true, we simply return that answer. Okay, that's the idea here. So let me try writing the code, and here if we look, I never explained the time complexities in recent videos, but I'll try to make sure that those things also I'll explain here from onwards. Okay, so let me write the code and I'll explain you like what is the time complexity and how we can further improve this particular one as well. Okay, but that particular piece of code I'll write it in next video. Okay. So see, what is the given here? So n are the number of vertices we have, and m are the edges, and this is the edge 2D where each element edge is represent edge between. Okay, so this is pointing to this, and since they are undirected, so both are pointing to each other, and they are starting from 1. Okay, so what we'll do is we will store we will create a adjacent list. Okay, and in the adjacent list what we'll do is we'll store the data in form of zeros. Okay, let me name it as adjacent, and let's create the objects. Adj dot add new. Okay, once we create the objects, what we'll do is we will explore the edges and fill the adjacent. Okay, these are in a form of array list, right? So let's get the array list of integer uh wait, edge from the edges. Okay, so in the adjacent dot get edge of edge dot get 0 minus 1. I am starting considering that we will start from the 0th index. Dot add edge dot get 1 minus 1, and vice versa we will add same as, because this is undirected graph. Okay, so it will be 1. For 1 we will add 0 as well, 0th node. Okay, so once we create the addition list, the first thing is, let's create a visited array, new int v, and now we have, sorry, this is n. Okay, now once we have the visited array, what we'll do is, for each vertices we will try to check if there is Hamilton path, right? So this will be starting from 1 to n, sorry, 0 to n, obviously, and I'll be having a DFS function where I'll pass this current vertex we have, addition list, visited, and what next? Do we need anything else? Yes, the n as well as the count. So currently it is 1, right? So yes, we visited. So here we check that if, so it will be Boolean kind of thing. Okay, so if DFS at any point in time returns true, we will simply return true, or else at for all the vertices we explored at any point in time we never get any answer, so we return false. Okay, so here what we will do is, we create the DFS function, Boolean DFS in current array list of array list integer list, and then int visited. So we can consider Boolean as well, but for this particular time I considered in format. So now first thing is, let's mark this current as visited. So I'll be marking it as 1, and each time let's fill these arrays, dot fill visited with 0, because we will check for all different vertices, and at any point in time if the visited is true, that is not going to happen, but okay, I think we can omit that line as well. Okay, so if total is equals count, that means we have all the nodes that we visited. Okay, so that's going to be the base condition. So from this one, what we will do is we return true. Okay, now the recursively we will try to check all the adjacent nodes that are there, vertices that we have for this addition dot get current, and we check that if this visited of adj node is equals 0, that means it is unvisited, then only we again call the DFS. But here in the DFS we it is returning Boolean, right? So we again check if the Boolean is returning true or not for addition nodes. Okay, for this addition node, we pass the adj same, visited same, total is also same, but the count is getting incremented now, as in we are exploring this particular one. So if this is giving true, then we simply return true. Okay, if DFS is true, then simply return true, or else let us suppose, from this particular same example, right, we check to 2, the neighbor of 2, and from here it is returning false ultimately. That means, like, once we the current is at 2, the one is, or total is not going to be count equals 2, right? So currently count is 2 and total is 5, so it is not matching. So again we reach into this for loop. For addition node of this current is actually 2, right? For 2, what are the addition nodes? That is only 1. For this 2, the addition node is only 1, and that is already visited, right? So this if condition makes sure that we are already checking if this addition node, that is 1, is true or not. That means it is unvisited or not. So that is visited, so we do not enter into this particular condition, then ultimately this should return false. So that way also we can think uh, all these kind of recursive calls. Okay, so we are simply returning false, but before that what we are doing is we are making sure that this current 2 is, we are marking it as unvisited. Okay, because at any point in time from any other possible route, if we reach there and we check that if it is visited, so that is not going to be the answer, right? So we have to mark it as unvisited, so we will fill it with 0. So I guess that's all from this one. Then let us see, like, from 2 if we start. Okay, the current is 2, so we mark it as true. So this is marked as true. Okay, and then we explore the RC node of 2, that is 1. So currently 1 is not visited. Okay, so from 2 I am saying is like for in this for loop for 0 that is 1 is already checked, it is not giving the answer. Then I is going to be 2, that is I mean if 0th index that will be 1, of course. So we check for the 2 all the possible nodes. So from 2 we reach to 1 and we mark 2 as visited, 1 as visited. The count is actually now 2. From 1 we reach to 3, 3 also marked as visited. From 3 we reach to 4, 4 as also marked as visited. From 4 we reach to 5. Now the count actually is keep on getting incremented, right? So whatever the count we are getting, we are just adding it into the 1, okay, in this DFS function. So that is getting keep on incremented and ultimately the count is actually 5. So we reach at this particular one, so this returns true. That means ultimately this will return to 4 4 4 4. From 4 it is returning to 2 to 3. From here it is returning true. From here it is returning true. So ultimately this reach to here and this will return true. So this is actually true. That means this particular function also returns true. So ultimately for at second from the second node we are getting the path. So we don't need to retry for other nodes, possible nodes. We simply return true from here. For all the other possibilities, if at all we are not getting, we are ultimately returning false. Okay, so here we are trying all the possibilities that we can get from, right? So this is getting exponential though. So the time complexity here is going to be n into n minus 1 into n minus 2 into n minus 3. So that's how it is going, right? So this particular for loop is n and this DFS call here it is taking n factorial. So n into n factorial is what ultimately n factorial is our time complexity in this particular function. Okay, so we can improve this one with the help of DP with the bit masking. That particular piece of code I'll explain it in another video because it requires some extra information and masking concepts also needs to be clear to understand that particular part of code. So yes, I'll cover it in another video, but for this in this particular video, so that's it. So let's compile it as well, right? So I didn't try that out. Let's see if we have any errors. No, let me submit it. Okay, so all tests are passed. So that's it from this video. I hope you got some understanding. Thank you for watching this video. Bye bye.